So let's have a look at exact sequences, especially short exact sequences. So suppose you have groups or modules or vector spaces or what have you. Let's call them GI, because I'm thinking of groups now. So you have a group, let's say G1, and here you have the 0 group, and then you have a map to G2 and to G3 and back to 0, for instance, and let's call this homomorphism from the group G1 to G2 phi1 and this phi2. And well, we do not need to name these this one and this one here. These are of course also homomorphisms, but there is only one way to map 0 to the group G1, and also there is only one way to map the group G3 to 0. So there's really no need to give a name to these two. So this sequence is called exact, or let's first focus on this point here. This is called exact at G2 if the image of the homomorphism phi1 is equal to the kernel of phi2, right? And it is called exact, so the sequence is called exact if it is exact at every point. Right? Point, of course, in this case means at every group here in our sequence. And let's look at a few examples. So what about this one? We map 0 to G1 to G2 and we're finished. So in this case we have only this homomorphism phi1. So what can we say about this is exact? What does this mean? Well, it means that the image of 0 in G1, which is of course 0, so you have this map here, and inside here in G1 is this image of 0, which is also 0. This has to be the kernel of this map phi1. So 0 is the kernel of phi1. So this is exact if and only if phi1 is injective. Right? Injective being the case if the kernel is 0, if and only if the kernel is 0. And well, we can do a similar thing for surjective maps. So let's look at G1 to G2 to 0. Just flipping the previous example over, so to speak. And now we have this phi1 here, and what can we say? One in which case is this exact? Well, I think you can guess it. This is exact if and only if phi1 is surjective. And let's look at this sequence and see why this is. Let's focus on G2 here, and you see that from G2 we have this map to 0. So everything in this group G2 is mapped to 0. And for this sequence to be exact at G2, if you look at our definition here, we need to have that the image of G1 under the homomorphism phi1 in G2 is the kernel of this map from G2, this map here, to 0, which is all of G2. So the image of G1 has to be waiting for the noise to go down. So we need to have that the image of phi1 is equal to G2, for this to be exact, and this is why this sequence being exact is equivalent to phi1 being surjective. So let's look at a dumb example. So what about this? 0 to G1 to G2. Well, this is exact if and only if G1 is equal to 0. Let's leave this as a very small exercise, just to get you in the habit of using these kinds of sequences. Just do the same analysis as we did here and conclude that this statement is correct. This is exact if G1 is equal to 0. And now we come to the case everybody is talking about, of course, which is the case of short exact sequences. This is the first interesting case, if you will. So let's draw such a sequence. We go from 0 to G1 to G2 to G3. So now we have 3 groups. And back to 0, and of course this is phi1 and this is phi2. And now we can combine our previous statements. So this one here, let's call it statement 1, and this one here is statement 2, to conclude that this is called a short exact sequence. So we can combine our statements from 1 and 2 to conclude that this short exact sequence has the property that this one here, this map phi1, is injective by 1, and phi2 is surjective. Right? This is a direct consequence. And well, there are two ways to get to a plethora of examples for this type of sequence, short exact sequences. Both are, well, you could call them cheating, well, because we could just do the following. let's say we have some homomorphism, right? So from some group G1 to some group G2 phi1, and now we want to have a short exact sequence. Well, why not take this one here? We just take the kernel of phi1 and we inject it in G2. Remember, the kernel is also a group, so the kernel now plays the role of this group G1 here in our definition of short exact sequences. So we inject the kernel in G1, and well, we use phi1 to map, but well, we do not map to G2, but we restrict the range to the image of phi1, so that this is automatically surjective. And well, you see that this is an example. You could say an artificial or dumb example of a short exact sequence, but it is actually a type of example that we will use and well, you can construct a similar example. If you take G, the group G1, and you take a subgroup G2 of G1. So now you do the following: you inject the subgroup G2 into G1, and then you go mod G2. So you project down from G1 to G mod 2, and again, this is by construction another example of a short exact sequence. And well, the first theorem to prove about short exact sequences, or about exact sequences in general, is that you can always subdivide so-called long exact sequences. So exact sequences that are longer than short exact sequences, you can always subdivide them or reduce them to a bunch of short exact sequences. And this is what we will show in the next mini lecture. For this one, thank you for watching. Don't forget to like and subscribe, and see you next time.